Welcome to GSSM GoSciTech Week 1. This is Astrophysics class.
Hello, this is Joseph Velasquez.
Caden Cruz.
And in our first day here, we learned about the scale and the math of the universe. And what I learned is that the universe is huge. You can go from the planet that you live on to Earth, and if you scale out, you can get to things like the observable universe, our Milky Way, and the Virgo supercluster, and many other large astral objects.
Using the base 10 logarithmic scale can help scale the size of the universe, all the way from a small atom to the size of the galaxy, which is about 10 to the 45th times larger. That is a 1 with 45 zeros. This just goes to show how large our universe really is.
Hi, I am Shirley Gardner.
And I'm Allie Abbey. And this week we learned that the seasons of the Earth are caused by the tilt of Earth's axis. Contrary to what some people think, the seasons are not hotter or colder depending on how close the Earth is to the Sun. Actually, the Earth doesn't move closer or farther away. It tilts, which will be shown in our graphs.
So in the graphs, they show the height over the date of the Sun in multiple locations around the world. The x-axis is the dates and the y-axis is the max height above the horizon. So if you're in either the northern or the southern hemisphere, a graph will look something like this or flipped. And it starts down low in the winter, goes up high in the summer because you're pointed towards the sun, and then back down in the winter.
Hi, my name is Celine.
And I'm Eliana.
Today we're going to talk about the history of astronomy. So a long time ago, ancient astronomer could already measure the Mars path. Later on, Greeks used the geometry scale to calculate Sun-Earth systems successfully. They were only 3% off. As the Earth-centered theory developed, tools got better. Copernicus proved geocentric theory was actually wrong, but it wasn't until Kepler's law that we knew the Sun is the center of the universe. Go.
Kepler's 3 laws of planetary motion describe orbits of planets around the Sun, and Kepler's 3rd law states that the square of the orbital period is equal to the cube of the semi-major axis. To further study Kepler's 3rd law, we did a project that helped to test if the law worked for objects orbiting the Sun as well as any object orbiting another object. By using Excel to plot the orbital periods and semi-major axes of the solar system objects and of Saturn's moons, we were able to come to the conclusion that Kepler's law is valid for all objects orbiting other objects.
I'm Daniel.
And I'm Miles. Astronomers use light to probe the matter in the universe. It can tell us the temperature and composition of different objects in space. Light behaves as a wave as well as a particle. Light as a wave of combined electricity and magnetism is called an electromagnetic wave. Light has a wavelength and a frequency. Almost all knowledge of the universe beyond Earth.
The first telescope was made in 1608 by Galileo. It was a refracting telescope. There are 2 types, refracting and reflecting. The first reflecting telescope was made by Newton, which uses a primary and secondary mirror and then focuses through a lens, and refraction basically uses a lens to focus the light. For the project we did, we basically did an experiment to see how lenses refract or focus light against the screen.
I'm Tomorrow,
And I'm Van.
and we learned about spectroscopy, which is the study of the spectrum of light, and we use spectroscopy in class to look at different materials to see the color spectrum. We had determined what materials or colors could be seen in the stars and talk about the graphs.
We graphed both continuous and line spectra. For a continuous spectrum, we graphed each color we saw and the area it covered in nanometers. For line spectra, we graphed where each line color was and how far apart they were.
Hi, I'm Eleanor. I'm Lauren. Over the week, our class learned about several topics, but stellar evolution was a topic me and my partner found the most interesting. But what is stellar evolution? Stellar evolution is the process of how stars transform over time. For example, a star can evolve into a white dwarf. After it transforms, the white dwarf may explode into a type La supernova. This happens over time, giving stellar evolution its name.
To give us a better understanding, we plotted a graph using the temperatures and luminosities of bright stars. This is called the HR diagram, also known as the Hertzsprung-Russell diagram. Using this helped us draw inferences on stellar properties.
My name is David.
And I'm Charlie.
Once a large star runs out of hydrogen to burn, it starts to burn all that is left, helium. But even that will run out. After that happens, the star is hot enough to start fusing helium into carbon, then neon, oxygen, and so on until it hits iron. The energy needed to fuse iron is more than the return is, and so the star loses heat and energy. The gravity crushes it until it explodes into a supernova, turning into a neutron star or black hole.
For our experiment, we studied Cepheids. Cepheids are unique stars that's luminosity rapidly grows and shrinks. We pulled their statistics into Excel and graphed the oscillation period over their absolute magnitude to compare how long a cycle lasts to their maximum luminosity. Based on the oscillation period compared to the speed of light, Cepheids can be used to check the distance of far galaxies.
Hi, I'm Toby.
And I'm Graham.
And the morning of our final day here at camp, we learned that the universe is expanding. The first person to notice this is Hubble when he was looking at the redshift in hydrogen lines from distant galaxies. And he noticed something odd. The farther a galaxy was from us, the more there was a redshift. So that meant that the farther galaxies were receding faster. And as scientists got better and better observations, the trend continued to show until it seemed that the farthest galaxies were moving faster than the speed of light, which shouldn't be possible.
This is actually possible because it's not the speed at which it's actually expanding, yet it's the expanding of space-time itself, which works irregardless of the universal speed limit of light itself. The expansion of the universe is analogous to, I guess, on Earth, we could, it's analogous to a rubber sheet with, let's say, coins on it. Expansion of the object spaces each coin far apart from each other, making it seem as though each coin is getting farther away from itself. So if Earth was one coin, it would seem as though other distant galaxies were running far away from it the further they were away. This is not true. This is only an illusion because it's actually for all different galaxies. A 3D version of this would be galaxies in space, three-dimensional space.
Thank you.